Introduction to related rates. Let's do a bit of review because related rates are word problems, so you're going to have a pretty good conceptual understanding of just how to interpret a word problem, as well as implicit differentiation if you're going to be able to make heads or tails of this type of problem. One tip is to keep in mind the types of units we use for different types of measurements. So if we look at length, that might be inches, feet, yards, miles, centimeters, meters, and many others, but notice that there's no exponents for these. Whereas if you see like square inches, square feet, square yards, etc., you're probably talking about area. If you see these cubic units, you're probably talking about volume. So sometimes you might see length, but not be quite given what type of unit you need. Sometimes you might see something like centimeters cubed, but not be told that it's volume. You'll just need to be able to see these things and recognize the relationships between the measurements and what they measure. So rather the units and the measurements for the units and what they measure. So we have related rates, but what on earth are rates? We've talked about it a couple times, but let's build it up again. So ratio is a comparison of two numbers or measurements. A rate is a type of ratio that compares numbers or measurements with different units. So if we look at this example, rather than just being 1/3, it's 1 cup of sugar per 3 dozen cookies. So our numerator is measured in cups of sugar, and our denominator is measured in dozens of cookies. And then a rate of change is a rate that describes how one quantity changes in relation to another. So it's rates, which means it's ratios with different units, but we have changing quantities. A common application of rates of change is speed, so where we have distance over time. So we're looking at the change in distance over the change in time. So distance and time are measured using different units, and they're both quantities that change. Slope is one type of rate of change. We have the average rate of change, which is something that you've probably been looking at since middle school. So we're looking at the slope between 2 points. And then what we've been looking at more in calculus is the instantaneous rate of change. So like at one moment, what is the slope of that tangent line? And we found that the instantaneous rate of change is the derivative of a function. So the derivative can give us the instantaneous rate of change at a moment. And if we look at this notation in particular, we see that we have the change in y over the change in x. So that means that we're looking at two different quantities that are changing and are measured in different ways. So when we say related rates, it's actually a bit of a shortcut for related rates of change. So if we consider the formula for the volume of a sphere, v is equal to 4/3 pi r cubed, this formula shows how the volume and radius of a sphere are related or equated in some way. So there's some sort of relationship between the volume and radius of a sphere, which means that if you change the radius or you change the volume of the sphere, the other quantity will change as well. When we're talking about related rates, most commonly we want to see how these quantities change with respect to time. So that means that we're looking at the change, that's what that little d at the top means, with respect to time, where we usually use that t to represent time. We can even write out time if we wanted. So this notation here means the change with respect to time, which means we're taking the derivative with respect to time. So we can take the derivative with respect to time of both sides of our equation. So we have the derivative with respect to time of volume is equal to the derivative with respect to time of 4/3 pi r cubed. And as we see, we're taking the derivative with respect to a variable that is different from the variable in our equation, and that's why it's implicit differentiation. Because some sort of relationship is implied, but we don't know what it is explicitly. Okay, so here is a related rates problem. Whenever you're working on word problems in math, you want to annotate in some way, whether you're writing directly on the problem itself or taking down notes of important information on a separate sheet. So, say we have a spherical balloon that's being inflated at a constant rate of 10 centimeters cubed, so 10 cubic centimeters per second. How fast is the radius of the balloon increasing when the radius is 6 centimeters? So how fast, that means we're looking at some sort of rate, is the radius of the balloon increasing when the radius is 6 centimeters? We have a spherical balloon that's being inflated. That means it's increasing in some way. At a constant rate, so that means whatever way it's increasing is constant, and that rate is 10 centimeters cubed per second, so 10 cubic centimeters per second. I always read it backwards in my head first. Well, if we look at this, this is a rate of change. In particular, cubic centimeters measures volume, so we have a change in volume, and seconds measures time, so change in volume with respect to time. Which means if we have a spherical balloon, we're probably looking at the volume of a sphere. So that'll be V is equal to 4/3 pi r cubed. And we want to know how fast the radius is increasing. So we're looking at the rate of that radius changing. So that'll be the change in the radius with respect to time. Particularly at that specific moment where the radius is equal to 6 centimeters. And we just have to be very careful here, because if we have a balloon that's inflating, notice that the radius of this balloon is changing. It is not always 6. At one moment it is 6, but is not always 6. So my volume is not equal to 4/3 pi 6 cubed always, just at one moment. Okay, and then let's just draw a little balloon to try to remind ourselves that we're working with a balloon. This particular problem doesn't need a diagram, but many related rates problems won't make sense without a diagram. So we have our balloon that's being inflated, though I suppose this one looks already tied off, and we have its radius. Let's look at some other information here. So when you're working on related rates problems and you're feeling a little bit stuck, sometimes it's useful to list out what you've been given and what you actually want to find. So we've been given the rate of change of the volume with respect to time. So we've been given dV dt, and dV dt is equal to 10 cubic centimeters per second. We also have some sort of equation for the volume of our spherical balloon. So V is equal to 4/3 pi r cubed. And then what we want to find is the rate of change of the radius with respect to time, so dr dt, is equal to something when our radius is equal to 6. Note how I'm writing this radius is equal to 6, so at r is equal to 6 in this find section. I'm not writing it in my given section, although I suppose you could, but I find it useful to keep my stuff that is staying the same and my stuff that is just at a moment separate. So once you have some information and you have an equation that relates the two things we're trying to find and what we have, so we are given dv dt and we want to find dr dt, this equation has v and has r. So we're showing how the variables themselves are related, and now we just need to find out how these rates are related. And the way that we'll find these rates, dv dt and dr dt, is by taking the derivative implicitly. We don't just want r, we don't just want v, we want dv dt and dr dt. So we have the derivative with respect to t of v is equal to the derivative with respect to t of 4, I don't know why I used a different color there, 4/3 pi r cubed. And we just have to be careful and remind ourselves, this is implicit differentiation. The t and the v do not match each other. And the t and the r do not match each other. They're different variables. The derivative with respect to t of v will be dv dt. And the derivative with respect to t of 4/3 pi r cubed will be that 4 pi over 3 times the derivative of r cubed, which will be 3r squared, but we're taking the derivative with respect to time, so that'll be times dr dt. Note that our 3's will divide out here. After you take the derivative, we can start substituting in the things we know and solving. So we'll substitute and solve. We know dv dt. dv dt is equal to 10 cubic centimeters per second. We also know r. R is equal to 6 at this one particular moment. And we don't know dr dt, but luckily that's what we're trying to find, and right now it's the only thing that's left. So we'll divide both sides by 4 pi times 6 squared. So we have 10 over 4 pi times 6 squared is equal to our dr dt. And then this will simplify a little bit. Notice how I didn't square 6 and multiply it by 4 right away. Sometimes these problems are a little bit easier if you wait until the division step to simplify things. So 10 and 4 have a common factor of 2. So we have 5 over 2 pi times 6 squared, which gives us 5 over 2 times 6 squared, so 2 times 36 is 72 pi. And then we just have to think about the units for this. So dr dt is the rate of change of the radius. So that means radius is a length, so that'll be a one-dimensional unit in some ways. So we're not looking at square units, we're not looking at cubed units, just regular inches, centimeters, meters. Since our spherical balloon is measured in cubic centimeters, that means the radius will be measured in just centimeters. And then time is measured in seconds. So the rate of change, how fast the radius of the balloon is increasing when the radius is 6, is 5 over 72 pi centimeters per second. I want to give you a cautionary tale of a very common mistake. Only substitute after taking the derivative. So only substitute in a momentary constant after taking the derivative. If we are to substitute this radius is equal to 6 centimeters into our formula now, we will get v is equal to 4/3 pi times 6 cubed. Notice that everything on this side is now a constant. So if we take the derivative with respect to time, we will get that dv dt is equal to 0. And this is because we have said that the radius is always 6. So we've said that the radius is not changing. We already know that is not true because if the volume is changing, these are related, so the radius has to be changing. So if we substitute in one moment, then our equation no longer makes much sense. We've said, sorry, the volume is always going to be this one thing. Our volume is always this for our balloon. It's not changing. So of course dv dt would look like it's 0. But this is not correct. Be careful that you only substitute after taking the derivative, or else you've changed something that's variable into something that's constant, and therefore not actually changing. So we don't actually have a rate of change.